First of all, I'd like to introduce myself. I'm Rory Bolt. I'm chair of the Technical Steering Committee for the Linux Foundation Software-Enabled Flash project. And at the end of this presentation, there will be slides that have pointers to where you can find more information on the Linux Foundation, the Software-Enabled Flash project, and opportunities to contribute. And we encourage everyone who's interested to sign up. So, once again, that will be at the very end, the call to get involved. Today, I'm going to be briefly introducing a product technology that we call Software-Enabled Flash. It is an open source project combined with hardware to deliver solutions that enable software developers to create differentiated offerings that maximize the value of Flash storage. So we'll be covering the software stack, software development kit, Flash translation layer within the software development kit, a quick run through the I/O path, and some future ideas that are currently under discussion within the project under the auspices of the Linux Foundation. And then, once again, at the end, the call to get involved and join the project. So, Software-Enabled Flash came about from speaking with practically all of the hyperscale vendors out there. And it's really a different way of thinking about Flash, right? So we wanted to get rid of the hard disk paradigms and expose the total capability of Flash. And for those of you who aren't intimately familiar with the internal structure of an SSD, typically there are many die within a modern SSD, can be hundreds of die. And the individual die themselves are actually fairly modest in their performance. The way Flash drives the astounding performance that you see in the specs and the benchmarks is through parallelism. And so Software-Enabled Flash is a mechanism for exposing the parallelism to software, giving it control over the parallelism that's available within the device, control over data placement and isolation of workloads to specific channels or banks of Flash die, control over the actual queuing and scheduling of I/O to the Flash die, and ultimately providing control for applications over the latency outcomes within their environment. So, this is a storage developers conference. What are the things we're trying to do for you storage developers, right? We want to deliver both hardware and software-based isolation. So, once again, we can provide total hardware isolation based upon dedicated Flash die on channels or banks. But we can also share those Flash die across isolations with policy that is software enforced to allocate either bandwidth or weights within the weighted fair queuing system for individual applications. We have a very sophisticated queuing model that can operate in traditional priority-based queuing, round-robin-based queuing, or weighted fair queuing. Right? So it's a flexible model, and within the deployment, you can have different what we term quality of service domains operating in different modes of queuing. Okay? Probably the biggest innovation is giving applications control over die time weighted fair queuing for the individual I/O operations. And this is all coming out on the auspices of a Linux Foundation project, which is fully open source, BSD, 3-clause license. There's an API, there's an SDK, utility functions, and full documentation, as well as a theory of operation for the SDK itself. And we'll be touching many of these different facets as we go through this presentation. Okay. At its heart, Software-Enabled Flash is a combination of hardware, which can be purpose-built hardware, along with a software stack, okay? It's important to note that the actual requirements for the hardware are not anything that's customized. So anyone should be able to create a software-enabled flash device using either their own controllers or third-party merchant silicon controllers. And in fact, if you were to go out just outside the door to the Kioxia stand, they actually have some software-enabled flash devices that are using merchant silicon in them. So it's not proprietary, it's fully open, okay? There are opportunities for customizing the hardware, and in fact, one of the biggest opportunities that we'll touch on a little bit later on in the presentation is the ability to make DRAM optional within the device. So a lot of flexibility in the architecture over the DRAM structure of the device. On the software side, you can see essentially three paths in this illustration from applications to the device itself. So most importantly from my perspective is the Software-Enabled Flash API and library extends all the way up into user space and allows user applications to interact and submit I/O, zero copy I/O through the IOU ring infrastructure from an application down to the device. So bypass all the kernel if you want in your applications and take full control over your latency outcomes and performance. In addition to that, as part of the SDK, we have a Software-Enabled Flash block driver, a reference flash translation library that interfaces with a standard file system that allows user applications that have been not modified yet, that aren't what we call Software-Enabled Flash aware, to run against a Software-Enabled Flash device. We'll talk more about how you can do that and what you can do with an unmodified application to take advantage of Software-Enabled Flash. But once again, the ultimate benefit is when an application goes Software-Enabled Flash native and interacts with the device directly. And then the third path illustrated here is that SDS block, software-defined storage block. So that's a nod out to hyperscale customers. They all run their own internal storage stacks. And whereas they may port some applications to be Software-Enabled Flash native, we believe that they will essentially modify their own software-defined storage stacks to interface with the Software-Enabled Flash library and offer these services in their current environment. Okay. So, moving on to the software stack. I'm going to be talking mostly.
Just a level set. So this is completely independent of NVMe Express?
Actually, that's a very good point. Thank you. So, if you'll notice in this diagram on the left, the block diagram, we're leveraging standards wherever we can. Okay, so like I said, we can leverage merchant silicon for the controller that has a standard PCIe interface that leverages NVMe Express to a high degree. However, we're introducing some new commands that are not currently in the NVMe standard. Long term, will they end up in the standard? We hope so. It's a long path to get there. But for any command where we could leverage an existing NVMe standard, we did so. So we have the notion within Software-Enabled Flash of something we call a virtual device. And a virtual device is a grouping of die, and you can specify their arrangement across channels and banks within the device. That maps almost directly to what's called an endurance set in the NVMe spec. So guess what? Our virtual devices are actually implemented as endurance groups using the standard NVMe commands. So wherever it was possible, we adopted the standard. There are some extensions that we will talk about that are new commands we're introducing that we hope to be standardized. Once again, they're starting off as an open source project, but the eventual path is through standards.
So one more level set. So this replaces the NVMe Express driver that's currently in
No, and we'll get to that too. All right. So this is a typical software stack. This is going to be the top 3 areas that we're going to speak mostly about. Storage applications, our high-level software development kit, and our low-level API. And we will now, I think, pretty much answer your question. So left-hand side here, storage application talks through operating system calls, may or may not go through a file system or page cache, goes to the NVMe driver and down to the device firmware. The right-hand side, using Software-Enabled Flash, our SDK and API, you have a direct path through, once again, the IOU ring mechanism introduced in kernel 5.19 and later of Linux. Direct path down to the standard NVMe driver, not replacing that. Optionally, we do have block driver interfaces so that programs that do not know how to communicate directly with Software-Enabled Flash can go through the standard block interface and speak to the device. Okay. So I've mentioned it several times, this application programming interface. These are low-level wrappers around the commands for the device, and it exposes primarily 3 new commands that are being introduced. And those are nameless write, nameless copy, and physical read. So in a Software-Enabled Flash device, you can set policy for your application, and that policy puts constraints on the I/O, right? So it can be directed towards a QoS domain, which is associated with a virtual device, which is associated with a group of die. And so by virtue of the fact that you're performing an I/O to that QoS domain, you've limited the die that that I/O can interact with, right? So in a sense, it's nameless because you don't get to pick exactly where your data is going to land. You can constrain it by policy, but the device is free to choose the optimal placement, optimal physical location for your writes, both for writes and copy commands. And the device returns to you the physical address at which the data was written. What this enables is a read path that does not go through translation. So you can get the full read performance out of the native Flash media itself. The final point on here is that Software-Enabled Flash is an open project. It has been designed since its inception to be cross-vendor, vendor neutral, as well as generationally neutral. One of the sort of dirty little secrets of Flash media is about every 18 months or so, the actual media itself changes fairly significantly. And so you have differences in the media between vendors, and you have differences in the media between generations from the same vendor. Software-Enabled Flash has been designed to abstract out the vendor and generational differences, but expose the native capabilities in terms of geometries and characteristics of the media itself. So, once again, it is a vendor-neutral project. Okay, the software development kit. This is a sort of a high-level overview of the software development kit. It is based on C with C++ bindings. We actually even have prototyped some Rust bindings for it too. We build and test against both 32-bit and 64-bit architectures. We also test both x86 and ARM architectures. So we're trying to be as broad as we can in terms of the platform and supporting multiple architectures. We rely on IOU ring. So that puts us in the modern Linux kernels, but it is built, the reference implementation is built upon Linux, all open source. We create a library that can either be built as a static or a dynamically linked library. We have event-driven callbacks. It's thread safe. Interestingly, it's lockless at this point, which is nice for performance utilization of the media itself. And it's highly modularized because the software development kit is a reference. It's something that you can use to build other things from. And so it was designed in such a way that we'll give you an example of how to do something, but we encourage people to create new and creative solutions based upon it. And so, for example, the reference FTL. It is a full functional FTL. I'm stealing a little bit of my own thunder here, but it was designed such that you could easily replace just the garbage collection algorithm of the FTL or just the lookup table, and it would be very clean for you to do that. And so I might as well just move forward to this because I've said half the FTL function there anyway. The software development kit has 4 main components. One is a command line interpreter. This interpreter allows you to interact with the device. Much like the standard NVMe CLI, there's an SEF CLI. This allows you to define virtual devices, quality of service domains, and assign policy to them. Okay? Interestingly enough, there is a built-in Python interpreter in the CLI itself, and so you can actually write Python scripts and send them to the CLI to execute. This comes in handy when you're trying to debug an application. We use it, for debugging the reference FTL, right? So we could write Python scripts that would read the raw data of our FTL and do consistency checks and the like as we were bringing it up. Okay. Second interesting part of the SDK is the FIO toolkit. I would be very surprised if people in this room didn't have some level of familiarity with the FIO utility. We created a Software-Enabled Flash native FIO engine so that you can create jobs that execute directly against Software-Enabled Flash devices and observe their performance characteristics without going through the operating system, without going through any translation, just speaking directly with the SEF primitives. And in fact, even supports zero copy, all right? So you can truly see what the bare media is capable of doing. We also have a series of device drivers that we've implemented in the software development kit. One of which, and we'll go into some of the other ones later on, one of which is a standard block device driver that is a Virtio capable, a QEMU driver, so that you can expose a Software-Enabled Flash device to a guest operating system as a normal block device. And so within that guest operating system, anything that can interact with a standard Linux block device, which is pretty much all Linux code, can interact with a Software-Enabled Flash device. So why is that interesting? Well, using the command line interpreter, you can set up multiple virtual devices or multiple SEF quality of service domains. You can assign different I/O weights to them. You can essentially define both hardware-isolated quality of service domains and software-isolated quality of service domains. You can play with all the policy of a Software-Enabled Flash device and then expose it to a guest as just a standard block device. You can run the same workload against 2 different guests, and you can observe the differences in application response to the different sorts of parameters that you've programmed in for both bandwidth control, latency control, or hardware isolation, right? So it's very, very powerful toolkit that allows you to evaluate the capabilities of software-enabled Flash without having to write any code at all. You simply define the quality of service domain with the policy that you want on it, expose it out through a virtual block device into a guest operating system, and then run a standard utility against it. Contrast that with using the FIO tool to talk directly to the software-enabled Flash device. It's a more efficient path, but you can do it either way. And then finally, the last component of the software development kit is the reference Flash translation layer. And this is what exposes out typical block semantics to applications, and once again, built to be customized easily. All right, we're going to briefly go down into each of those four major areas, starting with the command line interface. As I mentioned, it is Python scriptable. It allows you to do sort of lifecycle management of the device itself and provision the device for applications, for virtual machines, for containers. This is an example of an actual command. This is a kind of a wordy or verbose command here. This is how a quality of service domain is created. So we're giving it SEF-CLI create, the verb there. What are we creating? A quality of service domain. The next two parameters there are just sort of housekeeping. S is essentially which device, starting from 0 if you have multiple devices in the machine. This is the first device. V is which virtual device within that physical device we're operating on. We're going to put a quota on there, and these can be soft quotas or hard quotas, so that you could have thin provisioning of a software-enabled Flash device. But where it starts getting interesting is that third line there, the number of Flash media queues, okay? So we're giving an application the ability to specify how many scheduling queues it's going to interact with on this quality of service device. And then waits for read operations, wait for erase, wait for program, wait for copy read. Notice there's 4 values. In this particular example, across the 4 values, they're the same, but those correspond to the 4 queues. So you can have different queues with different weights for the different I/O primitives to control, once again, bandwidth and latency outcomes. Likewise, you can prioritize I/O by essentially favoring one of the queues and using it for, say, metadata writes or critical writes versus other queues. The last part of it at the bottom is assigning default queues for different primitives. So in this example, read operations would go to Q0, program operations to Q1. This is a hypothetical example. You could have other arrangements here. You could have them all go to the same queue if you wanted to. But these are just the defaults. There is within the API the ability to, on a I/O by I/O basis, override the defaults. So, if you have something that is an administrative task that's critical, you can override the default queue that it's going to be put on, and you can overwrite the default weights that are going to be used in scheduling that I/O. So extremely flexible and a high level of control over your I/O within the device itself. The FIO tool, I kind of got ahead of myself as I tend to do, but it allows you to explore all these different configuration options, right? What are the effects of separating reads in one queue and writes in a different queue? What are the effects of altering the read versus write weights or the erase rates? What are the effects of defining a quality of service domain with software-based isolation versus hardware-based isolation? You can do all that, explore all that configuration with just the CLI and the FIO tool without writing a line of code. Okay? So this allows you to essentially prototype your expected performance with a particular configuration. And Open project, full source code for this, full source code for everything included that I'm talking about today. It serves as an example of how you take a application that was designed to do file or block-based I/O and how you would change that into an application that speaks SEF primitives. So once again, it's a great example for learning the basics of converting an application to software-enabled Flash. All right. Next part of the software development kit are the Virtio device drivers. I mentioned previously that we have a standard block driver. We also have a ZNS driver. We actually have a third different virtual driver that was developed for a particular hyperscaler that had their own custom FTL. So once again, software-enabled Flash is focused on managing the media, and it's pretty much neutral to whatever higher level protocols you want to implement on top of it. So we can implement block protocols, ZNS protocols, custom FTLs for a hyperscaler, or as should be fairly straightforward to make this leap, you could create an object store on top of these primitives fairly easily. So once again, the purpose for creating these Virtio device drivers was to enable people to test real-world applications on SEF devices using different policies and configurations of the timing parameters, the waiting parameters, the die geometries, and be able to do all that without having to alter any of their source code at all. Okay? The final thing, and we're going to spend a little bit more time on this, is the reference Flash translation layer. So once again, many of you are familiar intimately with Flash media, but you may or may not have written an FTL before in your life or know what's going on underneath the covers. Fundamentally, Flash devices are very different than disk devices. They do not support overwrite in place, so you can't just write over a sector that you'd previously written. You have to erase it first, and interestingly enough, the granularity of erase is different than the granularity of write. So typically, you erase in very large chunks called blocks, and you write in very small chunks called pages. And so when you want to reuse a block or overwrite a block, you write the data into a new location, you invalidate the old location, and then you have to have something that comes along in the background that performs garbage collect, harvesting those obsolete storage locations, moving the data that's still valid within that block to new pages in a new block so that you can erase the entire block and reclaim the space. So all this is done by this reference FTL. It is a full-featured FTL, and it was, once again, built for modularity and expandability, right? So what are the tasks, right? Well, you want to handle read and write via logical block addresses, right? Flash doesn't have a logical block address, so the FTL performs that mapping of a logical block address into a physical location in Flash. Placement IDs, these are also known in industry as streams. So the reference FTL allows you to have 16 placement IDs. And what a placement ID is essentially a contract between the device and an application that you're going to put data with the same placement ID in the same physical block. And you're not going to mix data with a different placement ID in that same block. So it's a way to isolate data from one another. Typical use for this is grouping data by lifetime, because once again, if data becomes expired or invalid or overwritten, you can't overwrite it, you need to invalidate it, and then when you want to reclaim the space, you have to copy the other valid data out of that block to a new location before you can reuse the block. So if you know all this data is going to have roughly the same lifespan, you can write it all to the same placement ID, and when it all expires, that entire block likely expired at the same time. You don't have to copy any valid data out of it, and you reduce write amplification within the device. So placement IDs, akin to streams, it supports 16 automatic placement IDs, and that's just a directive you place in the write command, say, this is placement ID 1 or this is placement ID 2, and it will route the data to an open superblock that is associated with data only containing that placement ID. In addition to these automatic placement IDs, there is manual allocation of blocks and manual routing of data to an open block that allows you to essentially have an unlimited number of parallel open write streams within the device if you need beyond the 16 stream capability. I've already mentioned logical physical mapping, superblocks, tracking superblocks and their states. So we've mentioned anyway, the physical blocks within the flash die themselves that are these large, essentially, units of data that are erased at the same time, right? So the life cycle of a flash block is it's erased, you write into it. Once you've written everything into it, you close it. After a while, if data within that block is overwritten, it becomes invalidated. You can then copy the valid data out in a garbage collect operation to a new location and invalidate the whole block, at which point it gets put back in the free pool where it can be erased and used again. So something's got to track the state of these blocks within the die. So the FTL is responsible for that. A little bit of a misnomer, but it's grouped in with the FTL, is recovering from power loss. I was actually in the DNA session earlier today, and they were talking about how DNA was kind of unique in that it has to encode the address with the data. I'm thinking to myself, well, flash drives have been doing this for decades, right? Because we have this flash translation table that allows you to translate from a logical address to a physical location that moves over time within the device. But that lookup table is the keys to the kingdom. And if something bad happens and that becomes corrupted, you need a way to be able to recreate the lookup table from scratch. And so the way SSDs do this is that they encode the logical block addressing information with the data itself, much like they were talking about in the DNA program earlier today, so that we can rebuild the lookup table from scratch in the event of what we lovingly call an ungraceful shutdown. Tombstoning of blocks, that's essentially marking data is invalid so that the space can later be garbage collected and reclaimed. And the last thing up there, we've mentioned it several times, that whole notion of having to pull the data that's still valid out of a block that's largely invalid and move it to a new location so you can reclaim space. But there are other various maintenance tasks within Flash, such as patrol reads in particular, which is just making sure that the charge within the cells hasn't degraded to a point at which you need to rewrite the data to ensure its integrity. It's a full-featured FTL. It handles everything you would expect of a modern SSD. All right? So the components of the FTL in a little more depth in what happens as a I/O traverses through the system. So at the top level of the FTL is what we call our block layer. The block layer provides a block interface to applications. Block layer interfaces with a lookup table, which performs that mapping from logical block addresses to physical block addresses. There's Superblock Management, keeping track of the state of the system in the media. There's garbage collection, and there's metadata persistence. And that is, we have this lookup table, we have this Superblock state information. When you shut down a system, you want to persist all that so you don't have to rebuild it from scratch every single time. If somehow it gets corrupted or damaged, then you resort to rebuilding from scratch. Okay, so this is the essence of issuing a block I/O through the SDK. Essentially, you call SEF-block I/O with a context data structure. This context data structure, it's an eye chart. You're going to get the slides. Don't feel like you have to see it all right now. It contains a handle because you can have many independent block systems on different virtual devices and different QoS domains. So which block interface are we speaking to? That's where the handle points you. It has a parent structure, which allows us to build up chains of these contexts to group multiple operations into a single completion. And why would you need to do something like this? Well, once again, the performance of a Flash-based device is based upon how much parallelism you can extract from the device. So when an application issues a read for a megabyte, performance, you would have striped that data across multiple flash die when you were writing it. So when you read it, that single 1 megabyte read is going to be broken up into multiple operations against several die that can be executed in parallel to make the system perform well. And those multiple operations are linked together through that multi-context parent structure there. There's a completion routine. There's a arbitrary argument that gets passed to the completion routine. It's all for the application to use. There's a logical block address, a logical block count, all fairly typical stuff, some flags. Couple things towards the bottom of interest. There's an IOVEC pointer, which is the description of the memory that's associated with this command, the count of the number of items in the IOVEC array, and an offset that allows you to effectively do scatter-gather I/O from user applications to the device. I guess one last thing I'll kind of call out here is the optional placement ID if you were doing that automated separation of data by placement ID. Next up is the lookup table. This is essentially, in the reference implementation, a lockless table, but it's a simplistic, entirely memory resident lookup table. Currently, it's 64 bits per entry, so you can have truly massive devices. The memory usage is a bit high for practical application, but once again, the purpose of the SDK was to illustrate how to do things in an easy to understand mechanism. It would be very, very easy for someone to page portions of the lookup table in and out of DRAM from the media itself. In fact, that's that last bullet point up there. It would be very straightforward to split the lookup table between host RAM and the flash within the device itself. So once again, it's a full functioning, lockless, very high performance lookup table. There are things that you could do for your own purposes that would be fairly straightforward. It would be easy to turn it into object store. It would be very easy to implement a zone namespace-like interface. And in fact, we have an example of that in the Virtio drivers. If you wanted to implement compression in your storage stack and make it a start and extent type structure, once again, very straightforward to do. The Superblock Management, talked about this earlier, but once again, the focus of Software-Enabled Flash is control over the media and the media's health and exposing out the parallelism. So we make the device responsible for choosing the best location to do these nameless writes, as was mentioned earlier. In addition to that, we've talked about Superblock Management. I'm not going to go over that stuff again, but all that Superblock state, including the validity maps, are what's used by garbage collection operations. Okay. The garbage collect module. So again, this is a standard feature of all SSDs that allows them to reclaim space. The interesting things here are it has a high water, low water mark aspect to it, where when free space drops below a certain threshold, it will automatically invoke the garbage collection module. However, applications can also control the timing of garbage collect. And essentially, they have control over, hey, this is a really good time to run garbage collect, or hey, please don't run garbage collect right now. Once again, garbage collect competes with user I/O for bandwidth and media access. So giving control over garbage collect is an important thing. Earlier, I introduced the concept of a nameless write. There's also a nameless copy primitive, and the nameless copy primitive is used primarily by garbage collect in the reference SDK, and it is a copy offload engine. So, it's not like you have to read the valid data out of a block all the way up into host RAM and then write it out from host RAM back into the device. No, you can tell the device, I want you to copy from this superblock to this other superblock, and here's a bitmap of the valid data that you need to copy. That's one mechanism that can be used with the copy offload engine. It also supports metadata tags, and so if you have an LBA implementation, you can say copy this list of LBAs from this superblock to that superblock, or you can apply filters, this range of LBAs or outside this range of LBAs. It can all be specified to the copy offload engine, and that copy will be performed within the device without affecting PCI bandwidth or host memory bandwidth, right? It's all handled by the device itself. And finally, the garbage collect module is highly modularized, easily replaced if you have other strategies you would like to use for garbage collect. So, garbage collect procedure. Basically, we're going to walk through all that data in the Superblock state. We're going to sort it by the number of invalid ADUs so that we can pick the blocks that have the least amount of valid data that needs to be copied to minimize the impact to bandwidth within the system. We're going to allocate destination superblocks. We're going to perform that copy in drive without using the host CPU, DRAM, or PCI bandwidth. And then we're going to update the translation tables and free up those blocks. Mentioned earlier, the metadata, the state of the superblocks, as well as the lookup tables, translation tables between logical addresses and physical addresses, they can be persisted through metadata persistence. The interesting thing here is you provide a pointer to the metadata you want to persist, which you call the persist functionality, and it returns essentially a root pointer to that data. And that root pointer can be stored in a special location associated with each QoS domain. Each QoS domain can have up to 8 root pointers associated with it that can be used for storing arbitrary user metadata. And this provides sort of that anchor point, that breadcrumb trail to allow you to, at system initialization, have a known location that you can read from the root pointer, and it will point to where your metadata is so you can initialize your lookup tables and state tables and then interact with the device. The final thing here in the SDK is instrumentation. We will have a keynote speech that will have a live movie of this heat map. This is actually a heat map that was created using our own instrumentation, with blues being reads, reds being writes, and you can see that there are 3 different areas of die. These are 8 channels, 4 banks of die with mixed read-write workloads, primarily read workload and primarily write workload operating in hardware isolation mode. The instrumentation is dynamic. If you're not using it, it doesn't cost you any overhead. It can do JSON output, really quite flexible. And then we have some future ideas for where we want to take the software development kit in going forward, one of which is ext4 on Ceph. The next is computational storage. We're beginning talks within the Linux Foundation project on incorporating and marrying computational storage with software-enabled flash storage, and then distributing write buffers between the device and host memory. Once again, early in the presentation, we showed that there was flexibility on the DRAM architecture of the controller. Many hyperscale applications are looking at having thousands of open streams, open superblocks at a time. Each open superblock requires a separate write buffer for it. And so you run into a problem where if you size the DRAM in the device for worst case scenario, then you have all this captive RAM in the device that you've paid for that you're not using except for in peak workloads. And so there's flexibility to share write buffers between the host hardware and the device itself to minimize the amount of DRAM you have to actually install on the device, cost optimize, and still be able to handle peak workloads. And so the summary here, we're trying to provide very fine-grained control over Flash to actual end-user applications. The purpose of the SDK is to provide an example of how to do it and make it easier to use and make it easy to evaluate without writing new code. And the reference software itself, all open source, full source, published, modular, extensible, and well documented. So, the call to action. We would love your participation. We would love new ideas for things you would like to see added to the SDK, other applications you think could benefit from directly interface with Flash media. So we have the source code on GitHub. Currently, it's just the API up there. We're just about to publish the SDK. In fact, I would look for more announcements close to the OCP conference, would be my best guess. SoftwareEnabledFlash.org, it's a place where you can go to monitor for announcements and get more information. Highly encourage people to join the mailing list if you're interested in developing for Software-Enabled Flash. And sign up for the open source Software-Enabled Flash project at the Linux Foundation. Right? So that's the end of my presentation. I typically go long. I think I went long again. But I'm open to questions either now or catch me in the hall afterward, because I did kind of go long. Sure.
Aside from God's question, that also needs retention base and other quality issue statements.
I'm so sorry. I respect the mask, but it really is muffling your voice.
Aside from God's question, SSD also needs retention and endurance requirements. Who's doing that?
Okay. So the question was, aside from things like garbage collect, there are retention requirements that are placed on the devices themselves. So when you're writing to a flash device, you're placing charge into some cells. That charge can leak over time, and there are various ECC mechanisms that are utilized to reconstruct the data if it hasn't degraded too far. And there are mechanisms called patrol reads for us that are used to check the health of the cells in the charge to see whether or not it's time to rewrite this data to a new location to essentially refresh the charge in new cells. And in Software-Enabled Flash, we essentially send asynchronous event notifications saying it's time to patrol these areas so that the applications can have a chance to do it at a time that's convenient for them. So we give them an early warning, hey, you should really think about patrolling this. It may be degrading. However, ultimately, if the application does not heed the asynchronous event notification, we will protect the media. We will intervene and perform the patrol and the movement if necessary.
So you have to know a lot of the self-physics. You have to know the self-physics of each vendor and each round of each node of each vendor and variations on.
So, a great question. I would think like, well, do I have to know the requirements of each vendor and each node or each iteration of Flash media? Because like I say, they're changing all the time. And the great answer about that is no, you don't. But to be a software-enabled Flash compliant device, the device has to know that and has to be able to give you notification, the early warning sign, if you will, that it's time to do it. And if you don't do it, the device has to do it for you. So once again, every single vendor's Flash is subtly different in its media. It leads to a lot of overhead for people who try to self-build their devices. All the hyperscalers have had efforts to build their own devices, and they found that it's just this geometric expansion of test across vendors, across generations, across nodes, to be able to handle the programming differences and the maintenance differences between these things. What software-enabled Flash is striving to do, and it's really sort of the core of the idea, is the device handles all those differences. The device knows its media, right? And abstracts out just the high-level notifications for things like, you should issue a patrol. And when the application issues the patrol down to the device knows exactly what are the steps to perform the refresh and say whether or not the cell health is viable, right? So we wanted to get rid of the low-level intricacies of Flash and yet expose out the full capabilities. Yes?
So if the device does do the safeguarding, does that change the physical location?
It can. It can. And so what the device will then do is issue an address change notification up, right? And once again, once that's serviced, it's a lockless mechanism that performs the update in the LUT. Yes?
From a higher level, what sort of an application do you propose would take advantage of this?
Okay, I can do some easy ones and I can do some harder ones. So, you know, all the hyperscalers are implementing their own storage stack, right? So, you know, even though I'm going to call out names here, but this isn't really fair because they all do it. You know, Google is based on Linux. But if you think Google is using ext4 for their file system in the cloud, no way, right? They have their own internal file system. And so, likewise, Google and Microsoft and Amazon is probably the poster child for this. They all have services where you can buy, you know, a database as a service or a key value store as a service or this as a service or that as a service. And all of those service applications are prime candidates to be able to extract out the full capability of the Flash. It's sort of a strange place that we're at right now. In many of these hyperscale environments, and there are other applications for this, but I'm primarily right now focusing on hyperscale. In many of these environments, their single biggest cost in their bill of materials for their infrastructure is the Flash, right? They're spending per box more on Flash than they are on DRAM or CPU. And since it is one of their highest cost resources, they're trying to extract every single last ounce of both performance as well as capacity and reliability out of that media. And so, things that we would think of as being an absolute requirement for a consumer SSD, like RAID across the chips in a device, is viewed by the hyperscalers as a tax, a capacity tax on them, because in their systems, they have to implement redundancy at the server level, right? So that they're mirroring things, typically once locally in the same data center and once remotely. And so they would rather have control over all the media, access to all the media, maximizing their capacity, not performing RAID across the die, because it's handled at a higher level in their system. So there's a lot of opportunity for them because they control the whole stack by changing their software-defined storage stack. They can leverage the advantages across multiple applications, multiple services. That's sort of the easy answer, but there are a bunch of other different applications that we're exploring, and some of them, I don't know. We're really looking for feedback from people on what they think would be useful. Things like, oh, come on, I'm having a senior moment here. Excuse me. Oh, come on, the database that everyone does. RocksDB. Anything that's log structured in nature, anything that does a log merge sort of thing, you could get rid of a whole layer of inefficiency of log on log, because Flash itself is essentially log structured at its lowest level. So many applications like that are being investigated, and we're looking for feedback on what people would like to see.
The only thing that makes me nervous is the operating system environment. You can crash easily, and you're trying to manage a metadata table based on the persistent media. That's one of the advantages of an FTL in a drive is you're protecting yourself from those kind of failures. Right? So this seems a little risky.
So, it depends on your architecture. It truly does, right? If you have NVRAM in the system, right? And so I'm not going to mention names because I might say things that I'm not supposed to say, but there are people out there that in their data center, every single box has some non-volatile storage, and when you do a write to that system, it's acknowledged once it's in non-volatile storage, and it hasn't even seen the device yet, but it's protected against a power loss, right? So it depends on your system architecture. Yeah. All right. A flip side of that, and I know I'm probably answering more than people want to hear, is power loss protection is very expensive for the drives at scale, right? And so if you have power loss protection at a higher level in your system, you can cost optimize by removing it from the drive. Yes?
What about US latency? How is maybe in this case SFA requirements?
So as far as performance is concerned, our target is to be best of class with current shipping SSDs. We actually think in some cases we can beat it because once again, the read path is no translation. There is no lookup on the read. It's a physical read. So yeah, I'm getting the boot, the hook, if you will. But thank you all. Really fun. And feel free to grab me in the hall.